Okay, we have a 2 kilogram ball of clay. It's traveling at 3 meters per second right before it hits and sticks to a 10 kilogram door. The door is 1 meter wide. The clay hits 80 centimeters from the hinges. If the door was initially at rest, how fast will it rotate once the clay hits and sticks to it? So if we're looking down on the door, here's the hinges, here's the door, here's our ball of clay. It's going to hit and stick to the door. If we consider the ball of clay and the door as a system, and the whole reason the door will rotate is because the clay hits it. The ball of clay is going to slow down because it hit the door. So the clay is exerting a force on the door is exerting a force back. And since the door is on hinges, technically the clay is exerting a torque on the door. They're both going to rotate together. Angular momentum needs to be conserved for this system as a whole, because what the clay is doing to the door does back, so the net result is no net torque. Okay, initially, the door is not moving, so the door does not have any angular momentum initially. The ball of clay is moving, so we need to figure out what its moment of inertia is, its angular momentum is. Now for the clay, we can do either I times omega to find the angular momentum, or we can use R times the perpendicular momentum to find omega. Both are equivalent. It doesn't matter which one we use. I know the ball of clay is not technically moving in a circle, but we can treat it as if it were moving in a circle at that instant to figure out how much angular momentum it has. We cannot equate the linear momentum to the angular momentum. They're related, but they're not equal. Okay? So initial angular momentum, R for the clay, times the linear momentum. Linear momentum is the mass of the clay times the speed of the clay. R of the clay is the 80 centimeters, so we'll do 0.8 meters. The mass of the clay is the 2 kilograms. The speed of the clay is how fast it was moving, the 3 meters per second right before it hit. And by the way, the I omega gives you the same thing. Because what would I be for this ball of clay? It's a sphere, but it's not rotating around its own axis. You have this ball of clay, you have the hinges way over here. So if you have a mass that's pretty small compared to the radius that it's moving in, how do we find the moment of inertia? mR squared. If all the mass is located at a certain distance away, which the ball of clay is going to be small compared to the 80 centimeters, then we can simply use mR squared for I. Omega would be V over R. We'd end up with mRV, because one of the R's would be canceled. Finally, the door, we can't use R times the linear momentum for the door, because it's not a point mass. So finally, we're going to have I of the door plus I of the clay as our total moment of inertia times the final angular speed. And again, we can't simply add the mass of the clay to the mass of the door and then just use the moment of inertia for the door, because the clay is not going to spread itself uniformly over the door. It's going to still be a ball. It'll be kind of flattened out, but it'll still be a ball. So we need to simply add their moments of inertia. If you look on the table in your book, what is the moment of inertia of a door around its outside edge? 1/3 ml squared. So this is the mass of the door and the length of the door. Mass of the clay is still mr squared. So omega final, the rotation rate after the clay hits, will be the RMV, so the 0.8 meters times the 2 kilograms times the 3 meters per second, all over 1/3, the mass of the door was 10 kilograms, the length of the door is 1 meter, plus mass of the clay is 2 kilograms, R is still 0.8. It stays where it hits. So please do this with me so we can hopefully agree on an answer. Anyone else get 1.04? Units. The kilograms are going to cancel. The meters, meter squared on top cancels with the meter squared on the bottom. That leaves us with per seconds. The radians are implied. Okay, so our units are radians per second on that. So angular momentum is going to be conserved in any collision. This is a collision. So any sort of collision that involves rotation, so an object either is rotating or starts rotating, any collision that involves rotation, angular momentum will be conserved. Angular momentum is also conserved if you have a system where the mass is just redistributed. So an ice skater pulling arms in, they'll spin faster because angular momentum is conserved. Questions on coming up with this? Yes. If you look in the table of your book, it tells you the moment of inertia of a door around its end is 1/3 ml squared.